Today in this video, we are going to create GPT directly from scratch, and we are also going to convert GPT into ChatGPT. Now, when I was studying about GPT myself, I realized that there weren't enough resources online. So I had to do a lot of digging and put all the pieces together to finally make sense of how ChatGPT internally works. So in this video, I have tried to provide enough detail for you so that you can even create ChatGPT directly from scratch and know its internal working. Though there is a prerequisite for this video, you need to have an idea about how decoder works in Transformers model. GPT is a decoder only model, so you need to have an idea how decoder in Transformers work. If you do not know about decoder, then click on the upper I button. It will take you to my video of decoder in Transformers. Once you have watched that video, it will be very easy for you to understand how GPT works and how ChatGPT works. So I'm excited for this video. Without further ado, let's get started. Imagine that you are a part of OpenAI's research team back in 2018, the team that published GPT. You want to build a model that can generate human-like text, whether it's auto-completing sentences, crafting creative stories, or even acting as a smart chat assistant. You have already seen how powerful transformers are, and you want to utilize its capability to capture long-range dependencies and process text parallelly. Before the advent of transformers, it was very difficult to generate human-like text, especially long text, with the help of just RNN-based models. But now with transformers, you think it is possible. So let's see how you try to use transformers in generating text. There are two main components of transformers: encoder and decoder. Encoder reads and understands the input text, captures its meaning and context, while decoder uses this captured context from the encoder and generates output one word at a time. At every step, decoder refers to two things. One is the output coming from the encoder and other is the decoder input. The encoder's output helps decoder to understand the user's query, while the decoder's input help it to understand what has been generated so far. Now this setup makes perfect sense for tasks like language translations, where you need to constantly refer back to the source sentence while generating the translated version. In language translation, you always want to know what was the user's input and what has been generated so far. Based on this, you can figure out what you need to generate next. But for our goal, which is to create sentence autocomplete model or a smart chat assistant, do we think we always need to refer back to the encoder's output at each decoder step? Does it really make sense to have both encoder and decoder for text generation? Suppose you provide the input once upon a time and you expect the model to complete it and create a story out of it. Now with the vanilla transformers, the encoder will process this input and feed it to the decoder, and decoder will generate one token at a time. At each token generation, the decoder will refer to the encoder's output, which has processed the initial words once upon a time. But think about it. Does the model really need to keep referring back to the initial prompt again and again? Once the story is in motion, the new context is already built through the generated words. Constantly checking the initial prompt again and again becomes redundant. It adds little value and only adds extra computation. Because let's say you are generating this word magic, which appears at a very later stage in this story. To generate this word magic, you probably don't need to explicitly refer back to this input again. All you need is the built story so far, not this initial prompt explicitly again. So what's the smart move? Do we really need encoder? We don't, and that's exactly what OpenAI researchers did. They removed the encoder from the GPT model. And GPT is a decoder only model. And here's how it works. GPT takes in the user prompt directly through decoder. It does not involve encoder. The user prompt is fed directly to the decoder, and the decoder starts generating text one token at a time. After each prediction, the predicted token is added back to the decoder input. So the predicted token A will be added here and quite will be added here, and this process will continue till the decoder has produced EOS token, which signifies end of sequence. So GPT generates one token at a time, taking in the entire built story to generate the next token. This strategy allows it to look at what has been generated so far and what it needs to generate next. This is a simple and powerful technique for text generation. GPT stands for Generative Pre-trained Transformers, and it's a decoder only model. Now let's see what is inside this decoder block. What are the layers of it? As GPT's decoder only model, this is how decoder looks like in vanilla transformers. It has 4 key components: masked attention, cross attention, feed forward network, and add and norm layer. Now if you look at this architecture carefully, you will notice something. Can you see it? What about this encoder's output that is going inside the cross attention? Cross attention needs output from the encoder as well as the output from this masked and add and norm layer. But we don't have encoder in GPT. So do we need this layer? The cross attention is useful when you want to combine information from 2 different sources, like from encoder's output and this output. Or if there is multimodal input, like one input is image and other input is text, then we can combine the context from both image and text and can generate a single contextual embedding using cross attention. But there is no such requirement over here and we don't have encoder. So we can remove this layer to simplify our decoder block and our model will look something like this. Now let's see if we need these layers as well. Masked attention. We need this layer because it's useful in training the decoder. This masked attention layer only allows the model to see the previously generated tokens and not the future tokens during the training. We have seen that during the inference, the decoder generates one token at a time and the generated token is appended to the input. Now this strategy is great but is not very useful for training. For training, you want to make all the predictions at once so that the training can be faster. And for this, during the training time, we don't want the tokens to see the future tokens because that is not going to happen during inference. If you don't understand what I just said, then no problem, because we are going to discuss this again later in this video. For now, understand that the masked attention layer only allows the tokens to see the previous tokens and itself, not the future tokens. For example, this token chased can only generate the contextual embeddings by looking at the previous tokens and itself. It does not have access to the 4th and the 5th token while in the masked attention step. Similarly, this 4th token only generates its contextual embedding by looking at the previous token and itself. This token does not have access to the 5th token. This makes the model to read the sentence from left to right. It does not allow reading the sentence from right to left because text generation only happens from left to right. So masked attention layer prevents seeing the data from right to left. And this is helpful during the training time. Okay, so we need masked layer. Do we need add and norm layer? Yes, of course, because it normalizes the inputs and stabilizes the training. So we need them. Do we need feed forward network? Yes, we do need it because it provides non-linearity to the model and also adds more model parameters to allow the model to interpret complex patterns from the data. So all these layers are required. And this becomes the simplified version of decoder, and this is one block of decoder in GPT model. GPT-1 model uses 12 such decoder blocks inside it. Here's how the data flows in GPT. Suppose that the input has 5 tokens. These tokens are going to be converted into word embeddings of size 768 dimensions. This number was 512 in the vanilla transformers used for language translation, but in GPT this is 768 dimensional word embeddings. These word embeddings are added with positional encodings. Positional encodings are also 768 dimensions, so we can easily perform an element-wise addition between them. This position encoding allows the model to understand the order of the words. Now this combined input is now fed to the first block of decoder, which processes them and outputs new set of 5 contextual embeddings, each one corresponding to the input word. These contextual vectors are much richer representation of the data that are based by looking at the sentence context, not just the words context. Now this output is then fed to the next block of decoder, and this process continues for 12 times until we get the final contextual vectors for each token. Now here's the fun part. We said that decoder generates one word at a time, but from this output we have got 5 contextual vectors. So how do we process them to generate a singular prediction? What we do is we simply discard the first 4 contextual vectors and we only use the final contextual vector to make the output prediction. Now, why do we discard the previous token's outputs and only use the last one? The answer is simple. Remember, we are using masked attention layer inside the decoder blocks. Masked attention prevents the word to see the future tokens. So these tokens have not seen all the words. They have not seen the future words. Only this last token has seen all the words in the input. So it only makes sense to use this last contextual vector to make the output prediction. This contextual vector is 768 dimensions. We pass it to a linear plus softmax layer, and this layer generates the final word prediction, which will be the next word in this input. This layer is basically represented by this formula. The X here is this 768 dimensional contextual vector of the last word. The W and B here are the weight parameters. The size of the W is equal to the vocabulary size, 768. I'm assuming that our vocabulary has 10,000 words. So when we perform a matrix multiplication of a W of this size with a vector of 768, we produce a final vector of the size equal to the size of our vocabulary. And all these numbers inside this are probabilities because we have applied softmax over it. Every index will correspond to some word in the vocabulary, and as these are converted into probabilities, we choose the index with the highest probability, and the word corresponding to that index becomes our output prediction. And this is how the prediction is made in GPT. This is pretty straightforward. If you understand how decoder works in transformers, understanding this should be a very easy task for you. Note that I have only explained the inference part. I have not explained the training yet. Training is slightly different and we'll talk about it next. If the prediction from this timestamp is the word end, then this and will be appended to the input and this new input will be fed in the next timestamp. And the process will continue till we generate the end of sequence token, which will stop the decoding process. Now I hope this inference is completely clear for you and you're curious to know how the training works. So now let's move on to our next discussion and see how the training works in GPT. GPT is trained in 2 phases. One is pre-training phase and other is fine-tuning phase. In the pre-training phase, the model develops a general understanding of both language and the world. It learns grammar, sentence structure, and builds the associations across the wide variety of topics. For example, if you train GPT on data about India, the model will learn facts about India's geography, culture, historical sites, cities, etc. Similarly, if you train it on math problems, the model will begin to understand the mathematical concepts and how to solve basic equations. This knowledge gets stored inside the model's parameter. So when the model sees a word like India in the input sentence, certain neurons in the network gets activated and it begins to recall everything it has associated with India. Let me show you how it looks like using a pre-trained GPT-1 model. I've downloaded the GPT-1 pre-trained model from OpenAI using Hugging Face. This is a free model which you can also download. I'll provide its link down in the description box. Using this model using Hugging Face is pretty simple. You just provide it a prompt and ask it to generate it. So this model will just complete the sentence. When I gave it a prompt, the largest city in India is, it completed this sentence as, in the eastern coast of India, it is more or less 2000 miles away from the bush. The land is mostly rice field. Now, this auto completion is not correct. But do you notice something here? The sentence structure and the grammar is more or less correct. It's not perfect, but it's still so much better. This is the most basic model provided by OpenAI, and it's not producing the output as we require, but still as a pre-trained model with a fewer number of parameters, it's still doing a pretty good job. But here's where it gets interesting. Let's see what happens when I give it an input like, where is India? I'm asking it a question, but its response is, he finally asked, and she remained silent for a good 5 seconds. So instead of answering my question, it just starts to complete it like it's a narration. It did not answer my question. Now, why did this happen? Because at this point, it's just a pre-trained model. It does not know how to answer a question. It only knows to complete a sentence. So when it sees a question like this, it thinks that there is some character who is asking the question, and this is how it should complete it. Most probably, it has been trained on a data of novels where the character asks questions. The model is not yet fine-tuned to respond to users' queries. It only knows to complete a sentence. So this is where we need to fine-tune the model. Fine-tuning is where we shape the model to do a specific task. The best known example is ChatGPT. After the base model has learned about the language and the world, we now teach it to how to behave like a chat assistant, how to respond helpfully, politely, and answer a question. We move from general knowledge to task-specific supervision. Instead of letting the model blabber freely and complete the sentence, we guide it to respond to users' queries with the correct answers. So now let's deep dive into both of these phases and see how pre-training and fine-tuning works in GPT. Let's start with the pre-training. The goal of this phase is to complete the sentence. And in this process, we want the model to develop a general understanding of grammar rules, natural language, and also the understanding of the world on which it is trained. So for this task, we will need two things. One is we will need training data. And second is we will need to choose a task on which we train the model. Note that in the pre-training phase, we do not want to manually label the dataset because we want to pre-train it on a large amount of data. If we get involved in the painful process of labeling the data, then training won't be possible or it will be extremely expensive or unfeasible. So we want to use the training data and task in such a way that we can use the data from general text like books, Wikipedia articles, news, etc. Thankfully, our goal is just to complete the sentence. So we can take any partial sentence from any text and just ask the model to predict the next token. This strategy is known as next token prediction. And here's how it works. The input to the model during training is a partial sentence, and we ask the model to predict the next token. We can take this one step further and can use the same sentence to create multiple training examples. This means that if the input is the cat set, the next token that we want the model to predict is on. If the input is the cat set on, the next token that we want the model to predict is the, and so on. This way we can create multiple training examples from a single sentence, and we can also use any sentence from a valid text. And we have created a large corpus of dataset for us. So the task is next token prediction, and the dataset is any text from books, news articles, websites, etc. But wait a minute. If we train the model on a data like this, for a single sentence, we have created 7 training examples. This way, we will have a huge amount of data for sure, but won't it take a long time for the model to train? I mean, in our discussion, what we were saying is we provide the input to the model as partial sentences and we only ask the model to predict the next token. This strategy is fine and will work, but it will be very slow because in each forward pass, the model is only learning to predict one token. Can we optimize this further and allow the model to predict multiple tokens in a single forward pass? During inference, we have no choice. We can only predict one token at a time. But does that also apply in training? Or can we make the training faster by predicting multiple tokens at the same time? The answer is yes, we can. And this is how the training actually works in GPT. Remember I said that if the input to the model is 7 words, then the model will also produce 7 contextual embeddings as the output. Now during the inference, we were discarding all the previously produced context vector and we were only using the last context vector for our next token prediction. But we don't have to do the same for training. We can use all the contextual vectors in training. And this will speed fast our training process. See, here's how it will work. Remember, we had a mask applied in the attention mechanism. This mask does not allow the tokens to see the future words. This means that if I am processing this token on, this word does not have access to the future tokens. For this token, the input sentence is only this much long. It has no idea about the future tokens. This masking will help us in training. If we make a prediction using the contextual vector produced for this token, then this token's output context vector can be used to produce the next token after this word. Because for the model, input is only this long. So this token's output prediction will try to produce the next token after on, which can be the. Similarly, if we use the token at this position, then for it, the sentence is only this long. And this token's context vector can be used to produce the next sentence that should appear after the word the. So as the model can only see the previous tokens and it is reading only from left to right, each position can be considered as a partial sentence and output from that token can be used for the next token prediction for that partial sentence. So the next token for the word the will be cat. Next token for the sentence the cat will be sat. Next token for the sentence the cat sat will be on. Next token for the sentence the cat sat on will be the, and this process will continue. This way, in a single forward pass, we can allow the model to predict multiple tokens. And the model training can be much faster. This is a clever design. Instead of breaking down the sentence into multiple partial sentences, we have designed the model in such a way that it can interpret a single sentence into multiple segments or multiple partial sentences. That's why masked attention layer is crucial in GPT. Without this mask layer, the model would attend to the future tokens and this kind of training would not be possible. Now remember, the training predictions can be wrong. So for the partial sentence the cat, the next token can be wet, which is not correct. And it's fine because the model is still learning. What we will do is that we will pass this entire input to the GPT model. GPT will produce all output tokens, which will be the next tokens for the partial sentences, and we compare these predicted tokens with what it should have actually produced. Comparing the target with the predictions, we will get a loss. Now in the backpropagation, we will use this loss to update the model weight parameters. And this is how training works in GPT. This is fast and scalable and it allows parallel processing, something that traditional RNNs did not support. This makes Transformers architecture so powerful. And that's why we now have a capability to train the model on a huge amount of data. So this completes our pre-training phase. I hope you're able to understand this. Now, the next question is, how do we convert this pre-trained model into a usable application like ChatGPT? So let's have a look how fine-tuning works. How can we fine-tune this blabbering machine into something usable like a chat assistant? In the fine-tuning phase, the goal is to make the model understand and respond to user queries. In the pre-training phase, the model has learned to complete a sentence. So when you ask it a question like, how do I boil an egg? It generally understands that this is likely a question narrated or asked by a character in some story. So it also completes it that way. This is likely because it has seen this kind of data so many times, especially from the books or dialogues. It did not get enough examples where the questions were actually answered. So for a pre-trained model, this is just another sentence that it needs to be completed, and the pattern it has learned is the questions are often followed by more narratives, not answers. So how do we fix this problem? Thankfully for us, the solution lies in the problem itself. Because the model has mostly seen this kind of sentence structure, so it completes it like that. So what if we train it on a data where a question is followed by a valid answer? Then the model will also learn to complete the sentence in this format. And that's what fine-tuning means. Fine-tuning is where we show the model on how to generate appropriate responses. This requires labeled dataset. Unlike pre-training, we cannot have an unsupervised learning where we can just provide it any random text and ask it to predict the next token. Fine-tuning has to be on a labeled dataset because we want to teach the model on how to respond. OpenAI hired many human workers to write thousands and thousands of high quality question answer pairs. Each team of the workers covered wide varieties of topics from science, tech, cooking, travel, humor, and whatnot. And these were experts in language. And that's why we see ChatGPT respond so well, because it's trained on such a high quality data. If you observe ChatGPT's responses, then you will see that it follows a certain pattern. It is because that the label data that these workers made had a specific format, and the model just adapted to that format. This format for GPT is polite, helpful, and detailed. That's why this fine-tuning was very expensive and time-consuming for OpenAI. They had to spend a lot of money to fine-tune GPT into ChatGPT. This is the format of OpenAI's fine-tuning dataset. They introduced two special tokens, user token and assistant token. These are two special tokens introduced during the fine-tuning step, which acts as markers between the user query and the assistant's response. The training data is in this format. The first token is the user token followed by the user query. Then we have assistant token followed by assistant's response. Now these two tokens also have their own word embeddings, and they are treated like any other token in the sentence. They go through self-attention layers, feed-forward layers, and generate their own context vectors. This is how fine-tuning looks like. The input data is passed in this format. And remember, GPT generates same number of context vectors in the output as the number of tokens it has in the input. The context vectors for all the tokens up till the assistant token is discarded. And we use the context vectors from assistant token onwards to make the predictions. The first prediction is made using the assistant token's context vector. This prediction is made using linear plus softmax layer that I had mentioned in the inference stage. All the predictions are made in a single forward pass. Some of these predictions could be wrong. We compare these predictions with the actual tokens that it should have predicted, and then we calculate the loss between them. We use this loss to update the model weight parameters in the backpropagation step. Notice how the target labels are left shifted, which means that the target for this is the word to, the target for this is the word boil, the target for this is the word n. So all the tokens are left shifted by one place. It is because we are training the model to predict the next word. As the model sees that in each training examples, these special tokens user and assistant appear at a certain position, it will start to treat them differently. It will understand its role in the training process and it will use them accordingly. Now there is one thing to note here which is very important. As the model is used to seeing these special tokens user and assistant at specific location, the model also expects the input in this format in the inference time as well. If you do not pass these special tokens during the inference time, then the model will be confused and it will not be able to generate response appropriately. So whenever you ask a query to ChatGPT like what planet is closest to Earth, ChatGPT internally adds these special tokens and then starts its decoding process. And as I had mentioned, the inference happens by predicting one token at a time. In the first timestamp, this input will be provided, which will generate the next token Mercury, and this will mark as the beginning of the assistant's response. Now this token will be appended to the input and it will be passed to the next timestamp. In the next timestamp, it will produce the second token, which will be again appended, and the process will continue until the end of sequence is generated. So this is how inference looks like in ChatGPT. ChatGPT will learn to answer user queries based on its own understanding. Even if it has never seen a question like what planet is closest to Earth in the training sample, it will still be able to generate appropriate responses. Why? Because in the pre-training phase, it has developed the understanding of natural language and the grammar rules. And it also knows about the world, like it knows about what planet is, what Earth is, and how to interpret this kind of sentences. Based on all of this, it understands what a sentence mean, like just how we humans can. And in the fine-tuning phase, we have trained it to generate responses in a certain pattern, and it will always follow that kind of pattern during the response generation. If the pattern is polite, then its responses will be polite. If we had only fine-tuned ChatGPT on sarcastic responses, then it would not learn how to be polite. It would always generate sarcastic responses. And that's how we make ChatGPT from scratch. Now, in the later versions of ChatGPT, they have extended it by adding custom functions and search capabilities. In that case, the fine-tuning data format would look something like this. We can add some context that will tell what the context of that assistant is. Like if you want to name an assistant or you want to provide a description of that assistant, then that context will go over here in every training example. This will help the model provide an identity to itself. And then we add some custom Python functions or search functions. The model will be trained to perform a Google search on this keyword and inject its output in the assistant's response. We will also train it to inject the function's output in the assistant's response. This way, we can extend the chat assistant functionality by adding much more powerful features. Now, obviously, this is just a high-level representation of the data format, but the original data representation used by OpenAI is something different. You can go to the supervised fine-tuning section of OpenAI and find the training examples that they expect during the fine-tuning phase. On OpenAI, you can use their pre-trained models and fine-tune it on your specific use case. Now, the later versions of GPT models provided by OpenAI are not open source, which means that they are paid models. You have to purchase their subscription to use that model. Though there are free alternatives available out there, I will provide all these details down in the description box, so do check that out. So this completes our discussion of GPT. I hope you are able to understand how ChatGPT internally works and you got enough mathematical details behind its working. I was quite surprised to know how such a powerful tool that has revolutionized the world does not have extremely complicated logic that you and I cannot understand. As we saw, a simple few layers can create the core of this model. I hope I'm able to spark some curiosity in you to know more about such models and its implementations. If so, do hit the red subscribe button so that you don't miss out on my future videos. Hit the like button if you found this video valuable. Share your thoughts down in the comment section to let me know how you found this video. And for now, that's it. I'll see you in the next one.